This is the final discussion for Unit 9 Kinetics. And here we're going to kind of take a more detailed look at how the collisions occur, like in what order do they occur. Because remember at the very beginning, we kind of talked about that our balanced molecular equation, it tells us what we start with and what we end with, but it doesn't really give us all the detailed steps that occur, and that there could be multiple ways in which we can get from one set of reactants to a given set of products. So that particular pathway is called a reaction mechanism. So reaction mechanism is going to detail for us exactly what collisions have to occur and what intermediate products are occurring through a sequence of getting from a set of reactants to a set of products. And so the key thing to look at here is that these mechanisms are composed of a set of steps. And these steps, we call them elementary steps. And unlike a balanced molecular equation, these elementary steps actually represent a collision. So the reactants in an elementary step are actually colliding. And because of that, because an elementary step is not a summary, we can use the equation of the elementary step to write its rate law. Okay? It's because the elementary step, it's not a summary, it represents an actual collision or set of collisions. And so that's why we can use our elementary steps to write the rate law for that step. Couple of terms here. Intermediate. An intermediate, this is a product or a compound that is formed in one step and that is used up in a subsequent step. So it's something that does not appear in the balanced molecular equation. The other is molecularity. Molecularity is tells us how many collisions are occurring in that step. So we have three possibilities. So unimolecular, that means we've got something that's just decomposing. Bimolecular means I have two things, and it could be two of the same things, or it could be two different things. And then termolecular means I have three things. And we really don't, because the probability drops down so low, we usually don't go beyond like a termolecular elementary step. So what we'll see in looking at this little table is that if it's unimolecular, right, we have rate equals Ka. So that's the rate law for that step. And then bimolecular, again, if we have two of the same thing reacting, that would be rate equals Ka squared. Or two different things reacting, in this case A and B, so rate equals Ka times B. And again, we can only do this because we are dealing with these elementary steps. And so similar fashion, you would get the rate law for the termolecular elementary step. So if we look here, so here's our overall balanced equation for ozone. And we give it a possible mechanism. It says it has two elementary steps in the possible mechanism. And so how do we know if this is a valid mechanism? Well, we're looking for two things. So one is, in order to be valid, if I add up the elementary steps. So think back to when we were adding up reactions with Hess's law. So if you have the same thing on the same side, they add together. You have the same component, but it's on opposite sides of the equation, we're going to cancel them out. So when we add all those up, it has to give us the overall balanced equation. And then the other thing is that the rate law of the slow step must agree with the actual rate law. And remember, we said that the actual rate law, that is experimentally determined, okay, to get the actual rate law. But in here, the rate law of the slow step, and we'll talk a little bit more about that, but the rate law of the slow step has to be in agreement with the actual experimental rate law that we have. Okay, so let's kind of take a look at that part of it. So the rate determining step. In a mechanism, you will have one of our steps that is going to be the slowest. And so it sort of makes sense that if I have a sequence of things occurring, that the part of the sequence that takes the longest amount of time to complete, that's going to drive how fast the entire sequence can occur. So the slow step in the mechanism is what we call the rate determining step. All right. Another couple of terms here, which we've talked about, a catalyst. Catalyst is a substance that speeds up the reaction without being used up. And so what you'll see is a catalyst is sort of like the opposite of an intermediate. A catalyst, it's going to show up as a reactant and then it will end as a product. So again, it won't appear in the balanced molecular equation, but that's kind of the difference. An intermediate, it's going to show up as a product, and then it will be consumed as a reactant in a subsequent step. So that's kind of how to tell the difference between a catalyst and an intermediate. Neither one of them will show up in your balanced molecular equation, but the intermediate, it's going to pop up as a product first, and then it'll get consumed as a reactant. The catalyst will show up as a reactant first, and then it'll show up as a product at the end. So it will also get canceled out. And an enzyme, a good way to think of an enzyme is it's a catalyst for biological reactions. All right, so catalysts, how do they increase reaction rates? The catalysts increase reaction rates by providing a pathway, a reaction pathway, with a lower activation energy. So that means that collisions that without the catalyst, collisions that would normally not proceed forward because they didn't have enough energy, that with the catalyst, those collisions would go forward in a reaction. And so again, more successful collisions, greater reaction rate on there. And so this is kind of a key diagram to look at, and that notice that the catalyst, it makes the little hill smaller, but it does not affect your delta E or delta H of the reactants. The products still have the same energy, the reactants still have the same energy. Okay, so let's take a look at, here's some data, and this has got like a little bit of a review in it. All right, so in looking at this, I know my rate law, so I have rate equals K, and in this case, I've got an X raised to some power, and I've got a Y raised to some power. So let's take a look. I'm going to use experiment 1 and 2, or no, 1 and, no, 2 and 3, there we go, 2 and 3 to evaluate X. So we have it's times 2 on the concentration, and the rate is no change. So that means it's going to be 0 order with respect to X. And then now we're going to look at Y. And to do Y, I'm going to look at 1 and 3. So there I have 1 and 3, or 1 and 2, sorry. That's times 2. And then here, that is also times 2. So it's going to be first order for that. So I have rate equals Ky, that's my rate law. And then to find my value of K, I'm just going to use experiment 1. So 7 times 10 to the minus 4 equals K. And then my Y is 0.1. So that's going to be, my K is going to be then 7 times 10 to the minus 3. And my units, because it is overall first order, that's just going to be seconds to the minus 1 would be my units on the K. All right, so that was just nothing to do with reaction mechanism, but that was like a little review for you there. Okay, so then the following 3 mechanisms have been proposed. So we want to evaluate them to see, one, do they add together to give us our balanced equation, which was 2x plus y yields z. So I'm going to just move this summary. So we have 2x plus y yields z. And then we also want to, our experimental rate law is rate equals K times Y. So rate equals K, Y. So it has to agree with both to be a valid mechanism. So first off, let's add them all together and see what we get. So this one, my M's are going to cancel. So this one does give me 2x plus Y yields Z. So it passed the first test. This one here, I get, the M's will cancel, and I get Y plus X yields Z. So automatically, we can knock out mechanism 2 because it doesn't add to give us our balanced equation. Let's see, M cancels, N cancels, and this one gives me Y plus 2X yields Z. So the first one and the third one are still in the running. So now we want to look at, well, what is the rate law for the slow step? So this one, for that slow step, it's bimolecular, and I would have rate equals K X Y. All right. So that one, the rate law for the slow step does not agree with our experimental rate law. So we can throw that one out. On this one, though, if I do rate equals K Y, so here it adds together to give us that rate, and the rate law of the slow step does agree with my experimental rate law. So this mechanism 3 would be a valid mechanism. Okay, here it says, given the following mechanism, determine the overall reactions. Let's take and add this together. So let's see, the N2O2, that's canceling. Anything else cancel? N2O, that's canceling. And so what am I getting? I'm getting 2NO plus 2H2, and that's going to yield N2 plus 2H2O. It says, are there any intermediates? Intermediate shows up as a product. So let's do an eraser on this. Erase the things that I canceled. So here I have this one, the N2O2, shows up as a product, consumed as a reactant. And then I have N2O, shows up as a product, consumed as a reactant. So yes, so our intermediates are dinitrogen dioxide and then dinitrogen monoxide. So it says determine the rate law. Now, here is, and this is for reaction mechanism, this is going to be kind of the most complex type thing that you'll do. Here, if I write the rate law for that step, what do I get? Well, I get rate equals K into O2 and H2. Now, the problem with this is an intermediate. we cannot have an intermediate in our rate law. So what do we do when this is the case? And this happens a lot. If the first step is not the slow step, then most likely you're going to have to do some work to get a rate law that does not include an intermediate. So how do we do that? Well, let's think about what's going to happen. If the first step is faster than the second step, in this case, what's going to happen to the products of the first step? Well, the N2O2 is going to start building up, building up, building up. And systems do not like that, to have that happen, to get this really great imbalance. It's kind of stress in our system. So what's going to happen, and that's the indication here, way we see that, is you see how we have like a little set of double-headed arrows there. And we're going to do more with those in the next unit. But essentially what that means is that the first step is going to start reversing. So rather than continue just building up, building up, building up that product, it's going to go in the reverse direction and start decomposing that N2O2 to make more 2NO. And that will continue to happen until it hits what we call an equilibrium, meaning the rate of the forward step is going to be equal to the rate of the reverse. And that's the key thing here. So if we look at, all right, so rate, we'll do F for forward. If I write that, that would be KNO squared, right? And the rate reverse for that would be rate equals K into O2. So now at equilibrium, those two things are going to become equal to each other. So K NO squared is equal to K into O2. Now, I can use this right here, that relationship, essentially that the N2O2 concentration is going to be, because we'll drop out the Ks. Those Ks are not going to be the same, but those Ks are constants. And so we're going to be multiplying or dividing constants, and you just end up with another constant. So it doesn't really matter that the K for the forward is not going to be the same as the K for the reverse, because ultimately they're all going to get lumped into one constant, rate constant. So I'm going to use that NO2 squared is equal to N2O2, and I'm going to substitute that in in my rate law for my slow step. So what that gives me then, let's move over here, is I'm going to have rate equals K, and I'm going to have NO squared H2. So that would be, now I have a rate law for the slow step that does not include an intermediate. So then what is the overall order of the reaction? Well, we go back to our thing, so 2 plus 1. So my overall order is 3. It says, what is the molecularity of the rate determining step? The rate determining step has two things in it, two reactants. So it is bimolecular. Okay. All right, so let's look at the next one here. Write the overall reaction. So let's take a look and let's see what's going to cancel. The Mn3 plus, Mn4 plus, and the Mn2 plus. Those are all going to cancel. So what do I get? I've got 2 Ce4 plus Tl. That's going to give me 2 Ce3 plus Tl3 plus. Then it says identify each of the components as reactant, product, intermediate, or catalyst. So let's look at the ones that stayed. So the Ce4, I'll put R for reactant, and the Ce3 plus, I'll put P for product, Tl plus R for reactant, Tl3 plus P for product. So now let's look at the different manganese ions here. So we're going to look, let me erase my little marks here so we can look at them again. All right. So now the Mn2 plus shows up here as a reactant and N as a product. That is a catalyst. The Mn3 plus, all right, is showing up as a product and it gets consumed. The Mn4 plus showing up as a product and then it gets consumed. So those are intermediates. It says assuming that a catalyst is involved in the rate determining step, what is the rate law for this reaction? So our catalyst is in step 1, and so we would have rate equals K Ce4 plus. You do not include the catalyst in the rate law. Okay, we don't have to do anything else like what we did before with the intermediate, but we would just write the rate equals K, then your Ce, and that was the 4 plus. Okay, so D, why is the uncatalyzed reaction so slow? So if we look at here, all right, without this mechanism that involves a catalyst, look at how many things we are having to collide together. We've got 3. And the more things that have to collide in a single step, then the less the probability is that that's going to happen. So that's why it would be really, really slow, because there would not be very many occasions where all 3 of those things are going to collide together at the same time with the correct orientation. So all those things that would have to happen, it's like even less likely that they're going to happen the more reactants that you have colliding in that one step. So that's why the catalyst is important here, because it basically gives a different pathway for it. All right, under certain conditions, the reaction, and it gives our reaction, is found to be second order in NO and first order in Cl2. So it's saying our experimental rate law is K NO2 and Cl2 to the first order. What are the relative rates of the 2 elementary steps under these conditions? Well, okay, so let's see. The slow step is the one that the rate law would match. So first off, we can see that rate equals K NO Cl2. That would be the rate law for that elementary step. Does not match. So we know step 1 is not the slow step. So let's take a look at what we would get for step 2. So step 2, again, we're going to have an intermediate in there. And so we got to get rid of that. So we're going to set the rate law of, we're going to do rate from step 1. We're going to do rate forward equals rate reverse to get something that we can substitute in. So we get K NO Cl2 equals NO or K NO Cl2 there. So now we're going to substitute in. We're going to substitute this in for that, and that gives me rate equals K, and I'm going to have NO, and that'll get squared because I have another NO in there. No squared Cl2. So that's our other confirmation that the second step is the slow step, because when we do the rate law based on that step, we get agreement with our experimental data. and said the rate of the reaction shown below was studied. It was found that the rate doubled when H2 was doubled. So remember, same, that means rate equals K, so it's first order in our hydrogen. It was also found that rate increased by a factor of 4 when the NO was doubled, so NO squared. Which of the following mechanisms are consistent with this data? So let's look and see. So here, the slow step is rate equals K NO H2. All right, so that's not in agreement. Here, with this one, again, we're going to end up with rate equals K into O2 H2. All right, so we got our catalyst or our intermediate in there. So again, we're going to do forward. So rate forward equals rate reverse. And so we get, and I'm just going to leave out the K's because they can't spot anyway. NO, NO. So I have NO squared equals into O2. So I'm going to plug that in and I get substituting K NO squared H2. Okay, so that the rate law agrees. Now let's make sure if I add these together, do I get the right equation? So I get 2NO plus H2 yields N2O plus H2O. And was that our original equation? Yes. Okay, so that one does. So this mechanism works. Here, let's see what we got. We get rate equals H, which is an intermediate, and then NO squared. All right. So now I've got an intermediate. So again, I'm going to do rate forward equals rate reverse of the previous step. And so I get H2 equals H squared. So H is going to be the square root of H2. So when I plug that in, I get K square root of H2 NO squared. Okay, which is also the same as saying H2 to 1/2 NO squared. So that's not, that one doesn't work. And then lastly here, if that's the slow step there, get rate equals K NO squared, which again does not match. So this one, the second one, was the only one that met our criteria for the mechanism.